Right, welcome to relative motion in one dimension. Basic idea is this. If you're in a bus, and the bus is driving at 50 miles an hour, and you hold a ball, how fast is the ball moving?
50 miles an hour.
If you throw the ball?
Well, what's the relative?
Zero.
No, you're just holding the ball in the
Relative to
bus.
that tree over there.
Relative?
Once you hit zero.
Or the array?
Right. It all depends on your frame of reference. From the person in the bus who's holding the ball is moving how fast? Zero. But from an observer who's standing outside the bus on the ground, how fast is the ball moving? 50. Okay. Let's change the question a little bit. We'll say that the person inside the bus throws the ball forward at 20 miles an hour relative to themselves. How fast is the ball moving relative to the person on the ground? 70. Throws it backwards. 30 miles an hour. Does that make sense? All right. So the key is motion is always relative to the reference frame that you're in, or to a reference frame. And the exact same motion, the motion of the ball, can be described as plus 20 miles an hour in the reference frame of the person in the bus, or plus 70 miles an hour of the reference frame of the person on the ground. You all did that in your head. How did you do it? What was the key realization that you had when you did this?
You have to take into account the direction and just blabbling in mind.
You got to take into account the direction and magnitude, yes, of what? Vectors of what?
The ball.
You're missing something here. You're describing the motion of the ball, I agree, the velocity of the ball. Right. If you think about it, if you want to figure out the velocity of the ball with respect to the person on the ground, what did you have to do?
Add the speeds together or subtract.
Add velocities. You had to add the velocity of the ball with respect to the bus together with the bus respect to the ground in order to get the ball with respect to the ground. Does that make sense? And these problems get tricky. In one dimension, they're just that simple. You know, if you want to go ball with respect to the ground, it's ball with respect to the bus plus bus with respect to the ground. Got it? What if you had a person throwing a ball on a bus, which is on a train, right? And you want to know the velocity of the ball with respect to the ground. What do you do?
Ball with respect to the bus, with respect to the train, with respect.
Ball with respect to the bus plus bus with respect to the train plus train with respect to the ground to get ball with respect to the ground. Got it? So the key is it's just adding vectors. All right, which is great and easy in one dimension. In two dimensions, it gets a little bit more goofy. Classic problem. I'm actually going to skip ahead in the notes. Crossing a river. Suppose a river is moving east at 5 kilometers an hour, and the boat is traveling 45 degrees south of east with respect to the earth, and the boat is heading 60 degrees south of east. What? What did I just say?
Words.
Words, right. Let's look at the picture instead. All right. So what I mean by all that is, let's take the vectors one at a time. What is the vector of the water with respect to the ground? What direction is it moving?
5 kilometers east.
5 kilometers per hour east. So we draw an arrow to the right. Good? Next, the boat is traveling 45 degrees south of east with respect to Earth. Okay, so first of all, what direction is that?
Southeast.
Southeast. Okay, so that's diagonal that way. Or, sorry, that way, maybe. Or maybe it's that way. Whatever, southeast. Wait, what were the two things I was talking about? Boat and...
River.
River.
No.
Boat and earth.
Earth.
Boat and Earth. So that's going to be the total. Wouldn't you agree?
Yeah.
Boat with respect to the Earth would be boat with respect to the river plus river with respect to the Earth. So that's going to be the resultant vector is boat with respect to Earth. Got it? Okay, which leaves one more vector, which is we did river with respect to the Earth and boat with respect to Earth. What's left?
The resultant.
No.
No, we already did the resultants.
So we need river with respect to Earth.
No, we just did that one.
Boat
Boat with respect to river, which is whatever the remaining was, 60 degrees south of east. So if you're going to add them together, remember the rules for tip to tail for vectors? Here's your start. This is your resultant. So, boat with respect to river plus river with respect to Earth gives boat with respect to Earth. You guys got how to do that? Most of the time on the AP test, if you get this, is going to be asked as a multiple choice question, and the problems are going to be at right angles. In fact, most of the homework questions in your packet are right angle problems. All right? Yes?
How is like the boat heading 60 degrees south of east? How is that?
The word heading. What does the word heading mean? Versus traveling.
Direction it wants to.
Heading is the direction. Oh, sorry, go ahead.
Just with the influence of the river, which way the river is directing it.
Heading is actually the direction the boat is pointing. Not necessarily the direction the boat is traveling relative to the Earth. Does that make sense? So you could point your boat, say you had different problem, say you point your boat straight across the river, but the river is flowing. Do you actually travel straight across the river with respect to the ground?
No.
No. What way do you travel? You travel a little downstream diagonally. Agree? So your heading is straight across the river, but the direction that you actually travel is downstream. Got it? So the heading vector would be straight across. The river would have a vector that's downstream, and the resultant is diagonal. The direction that you actually travel with respect to the Earth. Does that make sense?
So the heading is boat with respect to
The heading, no, is boat with respect to river, actually. The heading is the direction of the boat with respect to the river. It's one of the vectors that you're adding up. All right? So if you're going to do a problem like that,
Then how can you draw a line for velocity of the boat with respect to Earth if that's not within the direction that it's going? It's just facing that way.
boat with respect to Earth is the direction that the boat actually travels.
Then what's the 45?
The 45 degree one, that is the 45 degree one.
The boat with respect to Earth is at 60 degrees. Or 30 degrees.
Mm,
But you have two arrows for boat with respect to river, boat with respect to Earth.
so the problem, did I get my notes wrong? I don't think so. The boat is traveling 45 degrees south of east, and the boat's heading 60 degrees south of east. So it's heading that way, and it's actually traveling this way over ground because the river's pushing it that way. Do you see it? Alright, I'm going to do a little bit simpler one. Let's say, here's your river. And your boat, you point the boat straight across the river. So what way is the boat heading?
South.
Straight across the river. What way is the river flowing?
To the right.
The river's flowing to the right. So what way does the boat actually travel? Diagonal. Does that make sense? All right, we'll pick this up more on